Hello everybody, welcome back to another video. Today we're going to be talking about decay processes. There's three main decay processes. There's alpha decay, beta decay, which is three forms, and there's also gamma decay, but we're not going to be talking about gamma decay today. We're mainly going to focus on alpha and beta. Okay, first before we start, it's important to know the isotope notation. So this is how it looks. So if we look like this, there's also sometimes a charge, but we're not really going to be dealing with that today. It's not very important with this. It's more of a chemistry idea than physics. So first off, X is equal to like the element you're dealing with. So that could be uranium, it could be gold, it could be oxygen, it could be nitrogen. Any of those elements, that's the symbol is going to be where the X is. Secondly, we have A. A is equal to the nucleon number. So nucleon is just the total number of neutrons plus protons, and that's what usually is the molecular weight. Lastly, the Z is equal to protons, and that is always going to be consistent for every single element. So like oxygen is always going to have 8 protons. Uranium is always going to have 92 protons, and so on and so forth. So if you ever want to know the amount of neutrons, you can always just use the nucleon number subtracted by the protons, and then you'll be left with the amount of neutrons left. So yeah, that's just important to know before we get started with decay processes. Another important thing is there's loss of conservation. The two main conservations we have to talk about is conservation of electrical charge and conservation of nucleon number. Those two are very important, but there's also a conservation in total energy, conservation of linear momentum, and conservation of angular momentum. But the first two are what we're really going to focus on when we're talking about decay processes. So to begin with, we'll start off with alpha decay. This is symbol for alpha. So alpha decay looks like this. So this is just like the backbone to like any problem you do should look like this. That's your starting element. And then I like doing this to show alpha. And then so this is your basically your parent nucleus. You can think of it as this one here. And then minus 4, and then your minus 2. And this is going to be your daughter nucleus, or your daughter element, you can think of it as. And you're going to add this is the alpha particle. So alpha, it's a helium that has 4 nucleons and 2 protons. And important thing is it has no charge either. So yeah, that's what alpha particle is. So yeah, so the alpha decay is when the parent nucleus is converted to a product as the daughter nucleus. So this is the parent, this is the daughter, and it also releases by the emission of a alpha particle. So this is the alpha particle, and it's important to talk about the conservation of nucleon number. So the nucleon up here, the amount of nucleons there is an A amount, and if you look on the other side, if you split it on the product side, you have A minus 4 plus 4, which is also equal to A. So is conserved. If you also look at the charge, you can think of a proton as a charge. There's a Z number of protons, we don't know, but on the other side, it's going to be Z minus 2 plus 2, which is also equal to Z or Z. So it's equal on both sides too. So it's conserved. That's a very important thing when dealing with any of these questions. It has to be conserved, the nucleon number and charge. So let's go on with a real example. So we're going to start off with radium 226. It has an atomic number of 88. I have a periodic table here to look off. And then there's alpha decay. So I'll give you some time. You can pause the video to tell me what the products are. And yeah, okay, I'm gonna start now. So first things first, we have to subtract 4 from the nuclear number. So you're going to be left with 222. And you also have to subtract 2 from the proton, and that is going to be left with 86. And off my periodic table, the 86th, the atomic number of 86 would be radon, which is Rn. And then you're going to add the alpha particle. And if you add up we'll do this once, but if you add up the nuclear number, you have 226 here, and here you have 222 plus 4, which is equal to 226. So we know it's equal. And also, if you look at the protons, they're also equal. Okay. Next, let's go on to, I guess I'll do here. There's beta decay. But there's actually 3 processes to beta decay. So I'm going to start off with beta minus decay. So this one is pretty similar, but obviously it's a bit different. So it always starts off with your parent nucleus, or the element you're starting off with, and it's undergo beta. Let's go undergo beta decay. So this time, this is your daughter nucleus is gonna gain a proton, and you're gonna shoot out an electron, and then plus this. So a neutron in the nucleus is converted to a proton. So here, a neutron is converted to a proton. So when this happens, an electron and an anti-neutrino is released. So this is the electron. I should put the negative one here. And this is the anti-neutrino. It's not very important to know like an anti-neutrino is. It's massless. It has very, very little mass, but it's almost negligible. But it's important to write because that it is there and it is also being released. Yeah, and an electron, everyone knows an electron, it's from the outer shells, and it's also getting released, and its mass is also very small, so um, that's why later on it'll be negligible. And then the main rule, as always, is conservation of charge and conservation of nucleon number. So if you look at the A values, on this side it's A, and on this side it's A. And here the proton is Z, and here Z plus 1 minus 1, which is also Z. So it's also balanced. Let's do an example. So right now we're going to start off with, let's start off with this one, PA91, and we're going to do, it's going to have 238 nucleons. And when it undergoes beta decay, quickly take a second to try it out. Okay, so I'm gonna start now. So the main thing about this one is the nucleon number does not change because we're just replacing a neutron with a proton, so it's gonna be the same. The proton number is gonna be added 1, so you're gonna have 92. So this is gonna become uranium. And of course, you have to add the electron and antineutrino. So as you can see here, there's 91 here, and there's 92 minus 1, which is equal to 91. So then the number of protons are equal to each other, which is the most important thing. Okay, let's do another example. This time it's going to become beta positive decay. So with beta positive decay, it's pretty similar. You always start with your parent nucleus, and then your daughter nucleus is going to lose a proton, but it's going to gain a positron. That's the main thing here. So a proton, so this time instead of a neutron, a proton in the nucleus is converted into a neutron, and then a positron and a neutrino are released. So in here, a proton is going to be converted into a neutron, and then it's release an electron and a neutrino. Important to realize this is a neutrino, and up here, oops, that's for later. Here is an antineutrino. Yeah. Okay, let's continue. So let's do a quick example here. 214. Oh, before I start, so also everything here is balanced. You're subtracting one here, you're adding one here, so you can end up with the same amount of protons, and then the nucleon is going to be the same as well. So let's do a quick example. This is 214, 83. This would be bismuth. So it'll be beta decay. So I'll give you a quick beta positive decay. Give you some time. You can pause the video, try it out for yourself. Okay. So this one, this will be 214 as well, but it'll be 84 here, and not 84. Whoops, it should be 82. You're subtracting one, and so you'll be left with lead, Pp, plus electron and anti. Just a neutrino. So yeah. Now we're going to go on to the final decay process, the final type of beta decay process. I'll just do it right here. The last one is called electron capture. This one is a bit different because the electron is now on the it's on the product side instead of the reactant side, like the other two. And we also start with our parent nucleus. So, whoops, that's the background. It'll be turning into the dark nucleus, which is going to lose a proton plus the neutrino. So yeah, if you so this one, then an electron is captured by the nucleus, resulting in a proton into in the nucleus turning into a neutron, and a release of a neutrino. So this one is similar to us. It's more similar to beta positive decay, as they're both protons into neutrons. So the last example would be, we're going to do another one with radium again. So we'll do 220, 88 radium. So what does this one become? Yeah, pause, try that real quick, and yeah, okay, I'm gonna start this now. So the nuclear number is the same, and then the proton number is one less, so it's going to be 87. So that becomes francium plus here. I should have done this before, but we'll just do it now. On this side, the nuclear number is the same, 226 on both reacting products, but the protons is 88 minus 1, which is 87. Here there's 87, so that's equal. So that's very important. And yeah, okay. The last thing before we go on to more practice problems that I have over here is we're going to be talking, actually just two more things. First is gamma decay. It's not very important, and this is when it's a change in the nucleus So, so a gamma photon is emitted when the nucleus is in an excited state. Excited state transitions to a lower energy state. So usually when it's uh, gamma decay is will happen following alpha decay or beta decay, but it's not very important, and it's just the release of uh, energy, and it's actually the most dangerous one uh, because can penetrate. Its penetration power is way stronger than the other two. So yeah, but that's all you really need to know about gamma decay, and it doesn't affect the nucleus in the way that the other ones do. Okay, lastly, we're going to go through this equation Q. So this is so Q values. Q values is the energy um, equation of a mass difference between the reactants and the products in a nuclear reaction. So it's going to be equal to. So this is the energy difference. And this is actually Einstein's E equals mc squared. But so then let's say how mass and energy are related. But the equation we're going to do is mass of reactants minus the mass of the products times c squared. So if Q is greater than 0, it's exothermic. If Q is less than 0, it's endothermic, which is very like counterintuitive if you think of chemistry, because chemistry is the other way around. But if you think about it, with this one, we're going uh, reactants minus products. So if the uh, if the products have more energy than the reactants, then you're gonna have an endothermic reaction because it's gonna be less than 0. And if your products have more energy, then it can't be exothermic because you're requiring energy and not releasing energy. But if your reactants have more energy or more mass, I should have said that previously too. But if it has your reactants and more mass, that means um, then your products it has more. It'll be able to release energy because um, it went from a lower energy to higher energy, so it's going to release energy, right? So it is counterintuitive, but if you look at the equation, it does follow the equation, which is the most important thing. So um, yeah, I guess we can go on some practical problems with this equation. Yeah, okay, let's do some questions. So these are some questions. Um, let's start with the first one. So this isotope 94 plutonium plutonium has an atomic mass of 239.0521556 use. The isotope is radioactive and decayed to uranium with a half-life. That part of the question will be for another video. But let's just look at question A. So identify the type of decay that um, this isotope goes under. So this is like all the other equations. First, we'll write the parent one. 239.94 pu, and we know it turned into 235.92 uranium. And of course, like I said multiple times before, it's really important to remember the conservation of charge and conservation of nucleon numbers. So to make this conserved, we need four more um, uh, uh, A values, or four more for the nucleons, and we need two more for the protons. And what does this look like? So this looks like an alpha particle that we need to put on this side. So we put I'll just erase here. Put an alpha particle on this side. Then if you just double check, this is 239 with A value. A value here is 235 plus 4, which is equal to 239. And then if we check the other one, 294. So you have 92 plus 2, which is going to equal to 94. So we know this is an alpha decay. And yeah, just a quick check. I have to make sure it's equal, it's conserved, and we did that. Okay, so last questions before we're done. So this is isotope of potassium, has this mass, is unstable. If this isotope were to undergo alpha decay, the atomic mass of the isotope resulting from the decay would be this. Okay, so the first question is just asking if potassium 40 undergoes alpha decay, what the atomic number Z and mass number A of the isotope resulting from the decay. So this one's pretty straightforward. You can try this one. Pause and try the video. Try before I continue. But yeah, I'm going to start now. So the most important part is start with our parent nucleus, is potassium, and it turns. We know that this is alpha decay. I'll put the alpha particle here. And I have a periodic table here, but if you didn't, you could just leave this as X. But we know we have to subtract 4 from the A number, so we're going to be left with 36. And then we have to subtract 2 from the atomic number, the Z value, and we're going to 17. And then we can just leave X here, but I have my periodic table, and 17 is chlorine, so I'm just going to write chlorine here. I can just double check. 36 plus 4 is 40. 17 plus 2 is 19. So they're equal on either side. So 17 and 36. Okay. Last question we're going to do, and this is the Q value question. Before I start, I should use some of the constants. First off, C. In this equation, we can use C as 231 point. So C is actually the speed of light, but 494 mega electron volts per U, because U is a mass number. It's not conventionally the way to write it, but it's easiest for this question. And the mass of neutron is equal to 1.008665 U. The mass of proton is going to equal to 1.00727. Oops, a little better. 72768. Okay, so now we know that. Like, first of all, they're very similar. They're almost the same, but the neutrons are slightly heavier. Okay, so how do we do this question? First, Q is going to equal to the mass of reactants minus the mass, the product, times C squared. So the mass. So this is the reactant side. This is the product side. The mass of reactants they give us in the question. It's right here. And then the mass of the products we have to calculate ourselves. The mass of the product is right here. Going to equal. So there's 7. So let's figure out the number of neutrons, and that's pretty easy because we did that at the beginning. 36 is a nucleon number, subtracted by the number of protons, or like the atomic number. So we're going to be left with 36 minus 17, which is going to be 19. So that's our amount of neutrons. So we can calculate the atomic mass on the right side. So if we do the mass of the proton is equal to 17 times 1.007276 U plus 19 times 1.008665 U. Total mass is going to be equal to 35.968307 U. And then we also, because it gave us because we didn't get the total mass of reactants, the mass of the alpha particle is 4.002603 U. If we do this question, Q is going to equal to the value up here, 39.963999 U. I think you look better. Minus these two values we got here, 35.9683 U plus 4.202603 U. And then we'll multiply that by 931.494 MeVu squared. It's a bit close to this. But yeah. If you do that all in your calculator, you'll end up with a value of negative 6.44 eV. And the most important part is this negative. This negative means it's endothermic and energy is required. Because energy is required, this does not spontaneously undergo alpha decay. So it's not possible. So yeah, that's everything that I have for today. In next video, I'll be going over half-lives, which is another part of nuclear physics. But yeah, thanks for watching and hope everyone has a great day.